Okay, welcome to the second part of our unit on vision. In this unit, we're going to talk about how we perceive colors and how colored objects behave under different lighting and why. So to begin with, we need to go back and think about our eyes a little bit more. And for that, we're going to look at the cones in your eyes. Remember, you have three color perceiving cones in your eyes. You have a blue one that is centered around 445 nanometers, a green one around 535 nanometers, and a red one around 575 nanometers. Notice that it's not a single color that the red cone is sensitive to. It's got a bandwidth to it. Same thing for the green, same thing for the blue. If you are colorblind, what happens is this distinction between the red and the green, or perhaps the green and the blue, is not distinct enough that your brain can tell when is red being tickled versus when is green being tickled. They're all getting tickled all the time. Okay. The other thing that comes into color is the frequency of the light. Remember, red light is low frequency, purple light or blue light is high frequency. I read an interesting article recently that magenta is not a real color because it does not have a frequency of electromagnetic radiation associated with it. And I will agree, there is no magenta in that spectrum. I would disagree, however. I think there is more to color than just the spectrum, because I know, for example, I can see yellow light when there's none of the yellow portion of the electromagnetic spectrum actually present, and it all has to do with how my eye works. And shortly we'll get into that a little bit more, but we need to get to where we can understand that. So the first thing we're going to do is think about primary colors and what the primary colors are. You might remember from school, the definition of primary colors is that they are colors that cannot be mixed. And you may also remember that red, blue, and yellow are the primary colors. You may even have made a color wheel out of the primary colors at one point in your school career. I'm going to disappoint you now. Here to burst that balloon, because red, blue, and yellow are not the primary colors. If I want to think about paint, the primary colors are magenta, cyan, and yellow. Okay. In a moment, I will show you a video on how you can take magenta and yellow and use them to mix red. And if I can mix red, it's by definition not a primary color. The other thing I want you to think about is if you go and buy ink for a color printer, what colors does it come in? Most often it comes in MCYK, magenta, cyan, yellow, and black. That's what the K is. Light, on the other hand, has a completely different set of primary colors. It's red, blue, and green. And I will show you in a moment a slide on how we can mix those to get different colors. Okay, so you may be wondering, why do we have two different sets of primary colors? It's because paint is a subtractive process. You're limiting the number of colors that can be reflected by mixing them together, while light is an additive process. If I shine red light on something, it can only reflect red. If I shine red and blue, it can reflect both red and blue. Okay. First, let's go watch this YouTube video. Now, I'm not actually going to show you all three YouTube videos in its entirety. I'm actually only going to show you a part of the first one. So pulling it up. Okay. So here we have a person with magenta paint, and they're going to make a lovely little square out of that. One thing I will say is that if you want to try this at home, you need to be careful with the magenta paint that you get, because oftentimes magentas aren't a true magenta. They have too much yellow in them to begin with. So instead of getting red, when you do a 2 magenta to 1 yellow like they're doing here, you end up with more of a red-orange. So watch what happens. 2 magenta to 1 yellow. Combine them together and you get red. Okay. Now, this video proceeds to take and add more yellow to this color so that you move through orange into yellow, kind of like making a color wheel. I'm actually going to skip ahead to where they start working with red. So now they're starting with a pure red paint. And look at the similarity between the pure red paint and the red they got from mixing magenta and yellow. It's not perfect, but it's spot on. Okay, so you may be wondering, if I can mix red paint, why don't they teach me magenta, cyan, and yellow in school? Why do they still teach red, blue, and yellow? Okay, a couple of things. One is some history. The 2 lists of primary colors, the magenta, cyan, and yellow, and the red, blue, and green, have historically kind of gotten mixed together and commingled and confused with each other. And because of that, they took red and blue from light, they took yellow from paint, and mishmashed them together. The other thing is, it's much easier to make a red paint than it is to mix a true red paint. So from that standpoint, it makes a lot of sense. In fact, I even had an artist at one point tell me she couldn't take paint from her box and mix red. And I'm like, okay, if you say so, I'll believe you. Cancel. That's what I want there. Okay. The other 2 videos show you how you can mix blue and green based on magenta, cyan, and yellow. Okay. If I take light and mix them, then when I start with red and combine it with blue, I get magenta. When I take blue and combine it with green, I get cyan. When I take red and combine it with green, I get yellow. If I combine all 3 primaries, I get white. And places where I have no light at all, I get black. Okay. Now, I said there's more to light than just the frequency, and this is the slide that illustrates that. Think about this yellow portion here. I have red light and I have green light. I have nothing in this picture, or causing this picture, if you will, that is due to something that is in the yellow portion of the electromagnetic spectrum. But I still see yellow. Hopefully you all do too. The reason I see yellow is because of how my eye works. I have a red cone and I have a green cone, and to perceive yellow, I have to tickle those 2 cones in some way. I can do it with red and green. Right? And remember, not everybody interprets how their eye works the same. So I had some friends that I was going across a bridge over the Mississippi when I was younger. And we looked at the bridge and they all said, oh, we're going across the green bridge. And I looked at the bridge and said, this bridge is blue, right? There was also the thing that went through the internet a couple years ago about the dress and what color was the dress. Same idea. Color perception is very much a how do you interpret what your eye is telling you type game. So summarizing what we've learned about light thus far. Oh, we can't summarize yet. Sorry. We're going to look at how our eye perceives color a little bit using this simulation. Here we have, I think of this as a lady. So we have a young lady. And if I shine red light into her eyes, you see, or she sees red. I really don't find the other illustration helpful, and I find it kind of creepy, so I'm going to go back to this one, but I wanted to show it to you briefly. If I turn up green, then her red cone and her green cone get tickled and she sees yellow. If I turn down red a little ways, I get an orange. Oh, sorry, wrong way. I get kind of a yellow-green. If I turn down green a little ways, I get orange. Right. If I turn green down and turn blue up, I see magenta. And again, I can turn them down a little bit, turn down blue, and I get not quite a red-violet, but it is trending that way. If I turn red down, I end up with more of a purple, but it's a very much on the blue end of the spectrum purple. And finally, if I turn green and blue up, I get cyan. If I turn green down, I get, you know, it's a not a true blue, but it's a fairly nice blue. And if I turn blue down, I get more of a greeny blue, almost a spring green there. At least that's how I interpret it, right? Okay. Now we can summarize. If I mix two primary colors together, I get these secondary colors for light. So red and green are yellow, red and blue are magenta, blue and green are cyan. And notice that the primary colors for light are the secondary colors for light are the primary colors for paint, and vice versa. If I want white light, I have to combine all three primary colors. I can do that by either putting them all on the wall, or I can mix a primary with its complementary, so red and cyan, for example. And if I don't want any light at all, I gotta turn everything off, and that will give me something that looks black. Right. Next, I want to think about why something would appear a certain color to me. So we're going to start by thinking about a green leaf. So if I shine white light on a green leaf, what does it absorb and what does it reflect? Well, if it looks green to me, that means green light has to be getting to my eye and it has to be reflecting green. And therefore, any color that is not green has to be absorbed. So the colors that absorbed are not green. So this would be not green. Or in other words, in terms of primary colors, this would be red and blue. And green is reflected. Okay. Now take a minute and think about what this means. Green leaves reflect green light. Okay. Therefore, if I put a green plant in a room illuminated with only green light, that plant will most likely die. Green light is not necessary for the photosynthetic process. Okay. Okay. Now let's consider another example. What if it is a cyan flower? So I start with all the colors of the light and I shine it on something that is cyan. Well, if it's cyan, that must mean it's reflecting blue and green to me, because that combines to give me cyan. On the other hand, the colors that are absorbed are not blue and green, not cyan, or in other words, in terms of primary colors, it absorbs red. Now, what I would really, really like to be able to do with you now is take and illuminate things in a particular color of light. And I use this slide for that normally in the class, where I have this big red square where I can put things into the colored light and you can see what happens and how they appear to change. But we can't do that here. So instead, I found some pictures. They're not perfect. So here we have a yellowish cube and a white sphere in white light. If I illuminate them with blue light, we see the white sphere looks blue because the white sphere reflects all colors, but the yellow sphere looks green. Now, from what we were just studying, there's no yellow in blue, right? In order to get yellow, I combine red and green, but from that standpoint, you would think that the cube here would go black, but it doesn't. So there's a couple of things going on. One is I don't think that the blue light here is a true blue. I think it is a blue that is slightly shifted towards the green end of the spectrum. I also, if I look at the yellow cube under white light, that doesn't look like a true yellow to me either, right? So I think that's why it didn't go quite as black as it should have under the analysis that we're doing. Okay, so I'm just going to put here that my thoughts are that this should have been black. I guess I should add. But it's not because of the color of the cube and the color of the light, not quite working well together. If I have a yellow cube and a white sphere, both of them look yellow under yellow, but again, the yellow cube almost looks orange here, and I think that's just the nature of how this cube is. It's not quite as yellow as it should be. I would have loved to have seen this cube under the yellow light, right? The other thing I will say is I don't think their yellow light is, it almost looks orange to me, if that makes sense. It's got an orangey tint, which would make a cube that is not quite yellow look a little bit more, right? Anyway, the next set work a little bit better. I have a blue cube, I have a red cube, and a yellow cube. If I take the blue cube, the yellow cube, and the red cube and put them under blue lamp, then the blue cube looks blue because it reflects blue. The red cube looks black because it absorbs blue. It reflects red, but there's no red to be had. And again, our yellow cube looks green, but look at this blue light. I mean, that does not look like a true blue to me at all. It's worse even than the one up here, right? If I take the red, blue, and yellow cubes and put them under a red lamp, the blue one looks black because there's no blue to be reflected. The red one, with the exception of the shaded side, you can't even hardly see because both the white background and the red cube are reflecting red, and there's no distinction anymore. And similarly with the yellow cube, because the yellow, remember, is a combination of red and green, so the yellow cube absorbs the green, which there isn't any of, but it reflects red. And oh, I just said that completely wrong. Let's try again on the yellow cube. The yellow reflects red and green. There's no green light to be had here, so it just reflects the red like the red cube. So again, it almost blends into the background. And lastly, if I take blue, red, and yellow under a yellow lamp, then the blue cube again looks black because there's no red to be had. Or, sorry, I am screwing this all up. Because there's no blue to be had, it looks black. It absorbs everything. Yellow is a combination of red and green, so the red cube reflects the red portion of the light and absorbs the green portion of the light, so it looks red. And yellow reflects both parts, therefore it looks yellow. This concludes this section and this unit, and actually the lectures for the course. I hope you have enjoyed.